this video, we are going to talk about how we can find the mass of a straight wire using integrals. So I want to start off with a case where our wire has what's called a uniform density. So along the whole length of the wire, the density remains the same. Okay, so I'm going to look at this example, which says find the mass of a straight wire that is 5 centimeters long with a uniform density of 12 grams per centimeter. So if I want to find the mass of this wire, let's draw a picture. So imagine I have this wire. It is just a straight wire and it's 5 centimeters long. So 5 centimeters in length. What this density quantity means is like every centimeter, if I go 1 centimeter along the way, 1 centimeter, that the mass of that portion is going to be 12 grams. And if I go the next centimeter, that's also going to have a mass of 12 grams. And the next one's going to have 12 grams and so on. So if I want to calculate the mass, we got to take the density and multiply it by this total length. So I'm going to write that underneath. We are going to take the density and multiply it by the length. So the density here is 12 grams per centimeter multiplied by the length, which is 5 centimeters. So one of the nice things that happens is I see the centimeters on top and the ones on bottom cancel, and that leaves me with 60 and then grams. Those are my units. Okay, and in fact, if I were to just keep adding up, okay, 12 grams for the first centimeter, 12 for the next one, and 12 for the third, and 12 for the fourth, and 12 for the fifth, 12 plus 12 added together 5 times, that is 60. Okay, so one of the things that you might remember about density, if you've seen it before, perhaps in like physics or science classes, usually with density, the units of it are mass on top, like grams, divided by unit of volume. So usually it's mass divided by a unit of volume. But if the object that we're looking at is like a wire or a rod, where either we're assuming it's like infinitely thin, or if it just has like a constant cross-sectional area. So even if it had some sort of thickness, but as long as that remained the same kind of all throughout, I can instead write the density having units mass per unit and divide it by unit of length, as we had in this example. That's why I was being divided by just centimeters, which are a unit of length. Okay, so now let's talk about a more interesting case. What if the density is non-uniform? What if it changes along the length of the wire? Okay, so what if now I have a straight wire that lies along the x-axis from when x is A to when x is B. So I'm going to start off by drawing a picture of the x-axis. So I will just draw my x-axis like this. And the wire portion we're interested in starts when x is A up until when x is B. So we are interested in finding the mass of this portion of the wire. And the problem tells me the wire's density is now given by a function. So this symbol here that kind of looks like a P, but it's a little slanted. This is a Greek letter. This symbol P kind of slanted like this is the Greek letter rho. Okay, so rho of x. Rho is a common symbol used for density. This density function has units mass per unit of length. And I want to find the mass of the wire. So how are we going to do this? So I'm going to use the idea, I'm going to try to estimate this mass first. And to estimate it, I'm going to chop up this interval into a bunch of pieces. Okay, so I'm going to let's write this. I'm going to chop up the wire into n pieces of length delta x. Okay, so I'm going to chop it up into a bunch of pieces. I've just drawn it chopped up in 4 pieces, but you know, that's just for the sake of my picture. All right, so now each of those pieces has a length of delta x. Each of these pieces has length delta x. All right. Okay, and I'm gonna, to find the mass of the whole wire, let's try to find the mass of each one of these pieces so that I can add them together. So if I want to find the mass of just the first piece, I'm going to call the mass of the first piece M1. I can, I'm going to use the idea of this first example to estimate its mass. Like I know the mass changes along the way, but maybe I can estimate just one number being its density. Because if I can do that, I just multiply the density by the length, and that would give me the mass. Okay, so I have to estimate the density because the density is changing along the way. So to estimate it, I'm going to take some x value in this interval. Doesn't really matter where I pick it, but maybe I'll put it over here somewhere, and I'll call this x value x1. And I'm going to plug this x value into my density function, and that's going to give me an estimate for the density on that interval. Okay, so I'm going to do rho of x1, plug that into the density function. So that is my density. And that is going to get multiplied by the length of that piece, which is delta x. So multiplying the density by the length, that gives me the mass. And it's just an approximation because the density changes throughout this interval. So by taking a test point like this and plugging it in, I'm just getting an estimate for that density. So overall, this is an estimate for the mass of this first piece. Okay, so I can similarly do that by picking, test values in each of these intervals. So maybe in the next interval, the test value is like somewhere over here, x2. Maybe the next one, it's like right in the middle, it's x3. And maybe in the last one, it's like way over to the left. Now I'll call that one x4. Okay, so overall, we are approximating, I'm just going to abbreviate approx. Let's approximate the mass of, just in general, I'm going to call it piece number I. And I will call that m subscript I. That is approximately equal to this density. The density when I plug in x subscript I getting multiplied by the length. All right. And now let's sum up the masses of each piece. I'm going to sum up the masses of each piece. Okay, what that's going to give me is an estimate for the total mass. So when I sum them up, I got to use sigma notation. I'm going to deliberately leave some space. Sum up, I'm going to go from I equals 1, that means piece number 1, up until n, which means piece number n. And I'm going to be summing up these masses. So over here, I'm going to put my rho of xi times delta x. So when I sum these up, right now that's an estimate for the total mass. If I want to make it equal to the total mass, we got to take a limit. We got to take the limit as n goes to infinity, which means we got to cut this up into an infinite number of pieces. So in front of this integral, in front of this sigma, I'm going to put the limit as n goes to infinity. And now that's going to be exactly equal. So we are defining this total mass using this Riemann sum. But as we've seen before, when we have this limit of a Riemann sum, we can write that as a definite integral. So my definite integral, the interval starts at a, it ends at b, and when I convert this to a definite integral, my function in here, which is this, that same function gets written, except we change this x sub I to just the variable x. So I'll get rho of x. The delta x becomes the dx. Okay, so my total mass, if I want to calculate that, I just got to calculate this definite integral of my density function. So to actually evaluate the total mass, we are going to use antiderivatives and then plug in, which means fundamental theorem of calculus. That is how we're going to evaluate this. All right. So we have just derived a formula for the total mass using a limit of Riemann sums to get this definite integral. If you continue to take more calculus, especially multivariable calculus, you'll see this type of setup where you use this limit of Riemann sum to, set up an equation for some quantity like mass. You'll see this all the time. Okay, so let's do an example. I want to find the mass of a rod of length 10 centimeters with a density rho of x equals x e to the negative x squared grams per centimeter at a distance of x centimeters from the left end. Okay, so let's draw a picture. So we have this rod. we have this rod here, and it says that it has length 10 centimeters. Okay, so I'm going to say the starting point, I'm going to think of this as 0 on the x-axis, and this other endpoint, I'm going to think of this as 10 on the x-axis. Okay, so if I'm trying to calculate the mass, we see from our formula that the mass should be just the starting point of the interval 0 to the endpoint 10, and then you put your density function, which is x e to the negative x squared, and then dx. And now we got to evaluate that integral. Okay, so I want to have you pause the video and try this on your own first. So pause this thing for 3 minutes to try it. So pause it in 4, 3, 2, 1, and try it. All right, hopefully you did that. Hopefully you paused it to try it. Let us talk about it though. Okay, so we can do this with u sub. I'm going to let u be the exponent, negative x squared, because then du is negative 2x dx. And I know this is going to work because I see this du in my function. I see the x here. And that's what du is. It's just off by this constant multiple of negative 2. But as we've seen before, even if it's off by a constant multiple, if the rest of it is there, as it is, x and dx, that's an indicator it's going to work. Okay, so let's isolate dx. I get du over negative 2x equals dx. And one of the ways I can do a u sub when I have these limits of integration is, right now that those limits of integration are in terms of x. Let's switch them so they become in terms of u. So I have the x value 0, I have the x value 10. I'm going to plug each of them into our u sub. So we'll get u equals, if I plug 0 in, I get just negative 0 squared, which is 0. If I plug 10 in, I get negative, and then parentheses 10 squared, which is negative 100. So this is going to give me, the bottom limit becomes 0, the upper one is negative 100, and then I have x times e to the u times dx, which is du over negative 2x. All right, I can pull out the negative 1/2 as a constant, and then I notice that the x up top and this x on the bottom cancel, so we are left with the integral from 0 to negative 100 of e to the u du. Okay, so now from here we can do the antiderivative. So I got negative 1/2. Doing the antiderivative of e to the u, that's just e to the u, and then we are plugging in the 0 and we're plugging in the negative 100. Okay, so if I plug in the negative 100, I get negative 1/2 times e to the negative 100, and then minus what I get when I plug in 0, and when I plug in 0 I get 1. Okay, so I'm getting this for the mass. One of the things that you might be thinking about is, wait, I thought mass can't be negative, but here I have a negative in front of this whole thing. But it turns out that e to the negative 100 is smaller than 1, so this thing minus 1 is another negative number. So this is negative, getting multiplied by this negative makes the whole thing positive. Last thing I need is units. So what are the units of mass in this problem? Well, it's grams. I got grams, and we got it. So in the next video, we are going to continue doing examples involving these applications, mass and average value.